welcome back to another iteration of Math Research Live with me, Charlotte Aten. So in a first for the series, I'm actually going to be doing the same type of thing this week as I was last week, which is that I'm actually going to be coding for this neural nets project. That there's an archive link pinned in the chat, and you can see it on the video here, and I'll post it in the YouTube videos description. But unlike last week, I hope to, now that I actually have everything set up again and have refamiliarized myself with what it is that I was doing last time I was working on this, I actually started to make some more progress at the end. And so this time I hope to do a lot more coding and a lot less of just generally talking trash and stuff. But still feel free to ask me any questions, and I'll try to do better this time. What I said I would do last time, which is not get too into the politics or the sociology of it, but try to actually write some code and maybe explain some of the math that's going on. So feel free to ask anything that you want, as always. And and I'll also mention that don't forget, we have this fun 3-hole donut emoji now, which is donut 3 if you want to type it in. And so make sure to make liberal use of that. And it was created by my partner, and you can see their Mastodon, Mastodon.art here. So be sure to check it out if you enjoy such things. I definitely don't have the artistic prowess to produce these emojis myself, so I really appreciate having that. It's a lot of fun. And I said I would do it in the first stream, and it is done. So I have lived up to that as well. Okay, so I'm literally right where I was before when I left off last time. I have not done anything else. I've had other things going on. It was my last week at the University of Denver, so I've just finally finished up my first postdoc there. But all week I've been thinking, I have so much fun, legitimately coding, not just like I have to write some amount of code just to do anything that I'm doing, like just day to day. But actually writing a piece of software that's not just like one-off scripts or like automating things, like it's not something that I've been doing quite as much over the last couple weeks, and I've been thinking, I really want to get back to this. I have so much fun, once I really get into it, and now I'm finally ready to do some real work on this, and so I figured I would just keep at it for the live stream. I've been thinking, I've been so busy getting things wrapped up, getting ready to move, but I figured I'd finally keep at it. So I hope that this is going to still be fun for people, and I will actually endeavor to write a lot more code this time. But as always, make sure to just let me know if you have any questions or anything. I'm happy to explain what I'm doing. The most immediate thing that I'm doing is I'm implementing some kind of graph and tree classes in order to use in the algorithm that I'm using. And I could just use like NetworkX or something to import a class that is already doing the job that I want, but I figured that I might as well do it myself, since I probably don't need all that machinery. I can just make it do exactly what I need it to do, and plus it's just good old-fashioned fun, and I hopefully can optimize it further, and really see where parts are coming in as I go on. Let's see where I was. So I decided I was going to make my own graph class, and it was going to be maybe loosely based on the one that had appeared elsewhere, somewhere. Let's see. Okay. Where was that? Oh, was it this? Is it here? Let's see. So the reason I'm doing this is I still need to implement these Dominion polymorphisms. Oh no, it's not here. This. this was it. Okay, so let's see what we have here. So so we have this graph that was okay. So this graph class was actually kind of playing the role of a rooted tree and a graph, and so. My first goal is to actually take that and remake it into maybe separate graph and tree classes that have their own module and have their own tests and stuff, just to make sure that that's all cleaned up. I wanted to do some things slightly differently, like what had been done over here before I commented it out was that. It looks like there were mutable data structures being used here, and so I kind of wanted to make this done in a way that was both immutable and was more lazy. So I decided to rewrite this over here, and also rewriting things I've found over the years is actually really good practice. Besides the fact that I just like to be particular and redo things in my own way that makes sense to me. It's also just with math and with coding, it's often a lot easier to actually do it yourself. Maybe using the other thing as a rough guide instead of just actually trying to absorb the other person's thing directly, because it just feels more natural when it's something you're building yourself. So let's see. I had actually made more progress than I remembered. So last time I was messing around with, okay, I want this iterable for the neighbors of vertex, and I think that this all worked the way it was supposed to. So B has neighbors A and C, edge set that. I don't have to, but I'm also not trying to rush myself. I do kind of think I want to make this string. I do think I actually kind of want to make the representative a little bit prettier, and so I think that the way I want to do this is. Let's see. So I think what I would like to do is I would actually like to make this prettier, and so here, let me just see if I can do this nicely. So I'm just going to experiment with something over here for a sec. I'm just doing an experiment over here to see if okay, that's the syntax that I want. All right, so not join, just join. Okay, and then So I can't actually assume that each of the vertices is already a string. So let me do that, and then that should give me what I want there, and then alright. Yeah, so then if I do this instead, nope, that's not what I wanted. That's fine. Yep, okay. Good. So that's just a little bit prettier, and I thought it would just take the time to actually do that, just to make it so that things look a little bit nicer. Of course, I don't have to, but you know, it's nice to have those things. Here's one of those cases where, you know, it's really a very similar, you know, piece of line of code that is used to turn the you know, the representations of the vertices and edges into something that looks, you know, how you would write a set like by hand or whatever more. And so of course I might be tempted to say, well, you know, really I just want like a frozen set to, you know, like a pretty print for frozen set or whatever. But that's something which is, you know, it's overkill. You know, you can abstract forever, but in the name of just getting things done. Oh, I forgot I have to actually, that's right, it's not exactly the same because I have to map into the next level as well. So actually I don't want that. I want what? I want to take self.edges and I want to, for each thing in it, I don't just want to cast it to a string. I want to take that thing and I want to make each of its entries string. Or does the map object not give me an iterable? That's a lambda. Is that not perfectly fine? Because I want to return that iterable. Alright. Fine, I'll just do it directly. Because it's just, instead of making it a string, I want to take that edge, which itself is a frozen set, and I want to return what I get when I map that over that. Is the problem that I need to flatten it? I guess that's maybe I get an iterable of iterables. Alright, fine. I'll just do it. I'll just do it this way. No, I just, okay, fine. Okay, now I'm feeling indecisive. How do I want to deal with this? that's not quite what I want. That's closer though. So now, of course, I forgot the inner parentheses. So I have to take this thing that I get, and I have to do this. So yeah, I mean, it's possible that another step of abstraction wouldn't be the most ridiculous thing to do at this stage, because clearly I'm doing the same thing to each of the frozen sets. But still, it's only really like 3 applications of this same kind of thing, and so that kind of makes me feel like, well, you know, at the end of the day, it's, oh, no, I don't, let's see, this plus this, oh, at the end of the day, it's really like, you know, it's not too much code to write out each separate instance of this, and so, you know, it's kind of one of those things where it's like, well, I could write something more abstract for just dealing with strings, but see, I mean, just doing it manually. Oh, and now I realize, actually, I do want it to be different anyway, so if I made an abstract function for turning frozen set into pretty frozen set, then I would actually have had to, make an option that said what kind of braces do you want around your pretty frozen set, because the inner ones are supposed to be, oh no, they're supposed to be ordered sets, because this is an undirected graph. Never mind. Anyway, that's perfect. That's fine. Okay, great. How are we all doing out there today? I feel like I usually get questions at this point, but maybe is it because this is me doing the thing that I was doing before, and so you're not wondering about what's going on? You're just right there along with me. Is anyone new to what's going on? Or, I mean, there's also the paper you can check out as well if you want to skim over it while I'm doing this. What do we think? Okay. Well, let's see. So I made that look nice, and that was nice. Let's see. I've done all of that. I have like the number of vertices and the number of edges, neighbors. There's some amount of documentation type stuff that I need to do. Let's see. The vertices are fine. The edges are fine. Okay, this attributes. This has its arguments. Okay, this is all fine. Maybe I'll document this slightly better. Documentation is one of those things where, like, it's like when people are learning to code, if you get someone who like gives you like a bunch of code with no documentation or very minimal documentation, and like even if they truly wrote it all themselves and they didn't like copy it from somewhere or whatever, it's like, okay, like that's, you know, like if the thing works, like that's great, but you know, it's concerning. But someone who produces beautiful documentation off the bat, like even aside from whatever the code says, like if you can follow what the idea is and like what the actual procedure is that they're trying to describe to you, that person's going to be fantastic. Like that's pretty much the way it goes, you know. So people are always like, oh, I don't need documentation. Like, you know, my code's very good. You know, I write great one-liners. Like everything's, you know, perfectly Pythonic and everything. But like, if you don't document your code, that's actually half of the use, you know. Yeah, if you document your if you do a good job at documenting your code, like that's a huge part of it, because like, you know, it's unlikely that even if it's you or the only person who's using your code, I promise you are not going to remember the detailed structure of your code for any like reasonable sized project in a year or two if you haven't touched it in a while. Even for yourself, it's really helpful, but especially when you're working with lots of people, like people are going to be maintaining your code and using it for other things, and being able to follow the idea that is behind what you wrote is actually very important. And it's the same kind of thing in math too, like giving the intuitive explanation for like, how do I actually remember this? How did I come up with this idea? That's in many ways more important than the actual idea itself, because you actually want to give people the ability to come up with similar ideas on their own. The theorem itself or whatever really is never, it's almost never the big thing. Like the fact that there are theorems that people get really excited about when they're proven. It's usually, like, occasionally it might be that it was just a really hard thing and it took so much effort to do, but it's really not the result itself. Usually it's the tools that let it be proven in the first place that are what people are interested in. Like, so, that's it, and that's that human level where you're communicating an idea to another person, and that's, a big part of writing code. That's a big part of doing math. Just seeing the code itself is not enough, and it's not really telling, like, the big picture story of, like, why did you write this in the first place. So yeah, I mean, it's important, and it's good to help your own organization too, because it helps you figure out what you're doing. So yeah, that's my rant about how writing well documented code is incredible. Like, if you can write well documented code, like, some people with coding or with math, some people are never fast. Like, not everyone is going to just be, like, super fast at doing this type of thing. It's not guaranteed. But if you're good at explaining, like, what you're trying to do, and continuing to make progress on that goal, then, like, you're gonna do great. Being able to apply, like, consistent, reasonable effort is a lot more important than writing a bunch of nonsense that is not documented and then having it work okay. You can't get by on that kind of thing forever. It might get you a good grade in your first assignment, but it's not gonna take you through life very good. Okay, so okay, vertex. Okay. Well, I'll just be lazy. Just say object. I mean, that's really all I can say at this point. So, yeah, my vertex is some object, and this is the vertex for which we find neighbors. Okay, and we return this iterator. Oh. Iterator neighbors the vertex in question. Okay. A lot of my documentation has a very stereotyped tone to it. I often am saying the blahs for the thing in question, but I think it's a good practice. Even though it's somewhat repetitive, I think it's a good thing to get in the practice of doing, and that's fine. It's just like how there's some boilerplate things that you want to say when you're doing math. It's the same thing with coding. Okay, so yeah, it's a graph with blah 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 blah. All right, so now I need to actually make a file that is the file that is representing this tree. Okay, and then I need to actually make the tree class. Oh, okay, so I'm going to actually make the graph is what I'm going to... So, I could make something that stores the graph as a JSON file or in a JSON file. But I don't think I want to store graphs in general. I don't think it's necessary for this algorithm. I think that what I want to do is just store trees, and the reason I want to store trees is because I think that I can do that more efficiently than I can store general graphs. So I wanted general graphs because I wanted a tree to be a certain type of, I wanted a tree to subclass graph, and I wanted trees to be a graph that had that property and had a root. So, I, me see. So the way that this was done here was I kept. Okay, so I wanted to make a random tree. Okay, let's see. So it's a graph. So at some point there's going to be something that's like making a random tree. New row. Think about this. So this is making a random tree. Yeah, and so it's adding edges. It's adding edges to a graph. But I'm thinking that, let's see, do I want it as an actual graph object? I was just kind of thinking like, okay, I'll have a graph and then I'll have a subclass that's tree, that are the ones that have a rooted tree that has the root. But let me think about this. I guess really I just want to have tree be a no, I guess I do want it to be a graph. No, I think I can't do significantly. I can't do significantly better than just storing the edges. I'm wondering how expensive this is going to be. I think I really don't need that many nodes. Don't need that many colors. Yeah, so maybe let me explain better what I'm thinking. So like there's kind of like, okay, here I'll actually go to the board. So like there's a couple different choices that I can make. And so like my student made one choice, but I want to redo things kind of in my own style as I'm integrating, because my student didn't fully integrate the code that he wrote into like the rest of it anyway, and because I know the bigger picture of the project, I'm going to take what he wrote and use it as the basis to write my own version of it, and in that process I might change some of how things are structured. And so one of those things was that like I was thinking, okay, I'll have a graph class, that is, it's a little bit, fancy, but it has basically, set of, frozen set of vertices, and frozen set of edges. And then I'll have a subclass of this, which is, okay, so these are the attributes it has, and then I'll have a subclass of graph, which is, here, maybe I'll do a different arrow, which is tree. And so trees will be graphs, but in addition to vertices and edges, they'll have a root vertex, because they're supposed to be rooted trees, and so that just means one of the vertices is labeled basically is the special one that the tree starts from. But of course, you can, if you just are given a graph that's a tree that doesn't have a specific root labeled, like if I don't know, whatever. I have like this or something, I mean, you can really choose anything you want. Maybe the way I drew it, you'd think, that's the root. But of course, that's, you could just say that's the root, and it's still, you could think of that as being where it starts from. There's really nothing special about any of the nodes in particular. But you choose one, and you say, okay, I have a root, and it's supposed to actually be a tree, so it's, it has to, be cycle free. And so, if I made a tree a type of graph, then there's a certain amount of space that's taken up by storing the representation of the tree. Like, let's call these nodes A, B, C, D, and E. If I store it as a graph, that means that my vertices are going to be the frozen set, which has, maybe these are strings, for instance. And in practice, I'd probably actually use ints, because that's like a, strings are a fundamental data structure too, but ints probably take up less space. Of course, as always, I probably really would do something in a lower level language if I really wanted to optimize, but I'm just trying to get the first working model of this still. Just want it to be fast enough that I can do experiments and convince myself and other people that I should spend more time on this, or maybe money if I ever get any money for this. That would be good too. So the edges would be, the order doesn't really matter, but like A B, B C, C D, C E, and maybe DC. Okay. And so, so that's a certain amount of space, and it would be the same for the rooted tree, except, the root would be labeled as well, and maybe I'd say, I'd just say, I don't really need that. Maybe I'd say, okay, the root's A, like maybe I'd say A is the, A is the root. And so, and I can either make this be a tree by construction, or I can guarantee that it's cycle free, but, I could even just maybe say rooted graph has a root. So I guess what I'm thinking though is that if I truly made a different tree data structure, then there's something that's slightly more efficient that I could do maybe, which is that, I mean, it's not really a huge difference, because like I could also say, well, I could have like a dictionary maybe telling me, I could have a dictionary telling me like, for each node, like just what are its neighbors, and if I had a rooted tree, I could think of it going in one direction, and I could say, well, like A goes to B, B goes to C, C goes to, D and E, right? Like I could say that instead. Although I don't really feel like it's a huge difference. And I think I do want to be able to iterate through all the neighbors for the algorithm that I have in mind. By these changes, do you mean like changing it from whatever my student did before? Or do you mean like the choice between like whether to use like this graph representation versus like using a dictionary style representation of the tree, or just a graph? Maybe a directed graph if you're thinking about this as being directed. Because, or if you just meant in general, like what are these choices affecting? So, I mean, none of these data structures in Python are going to be like super efficient, because like this is something that can be done extremely well at a low level of actually like more directly manipulating the memory itself, and not like using these like large data structures that all objects and object-oriented programming languages are to store this stuff. I still, there's a balance between like, not caring about efficiency at all and saying, okay, well, in order to start this project, I need to write a library in C or something. There's a balance, and that balance is usually trying to use immutable data structures and trying to do things lazily, like using iterators as opposed to lists, like preferring like tuples are better than lists if you can use them, and iterators are better than tuples. Like that's kind of the idea. Because I can't quantify this exactly. I don't know if there are any like large-scale estimates that you can look at. I mean, of course, I could do experiments to show you experimentally what the difference is. But the general rule is that immutable data structures take up less space. They'll take less memory to access. When you access things lazily by just using iterators instead of actually producing a complete list of neighbors, say, then you're using resources more efficiently, because your program can progress on to the next step of what it needs to compute without having to go through the list. Maybe I just needed to find one or two neighbors of a vertex in my graph. If I have a neighbors function if I have a method for my graph class that produces the entire list of neighbors, if my graph is big, even if it's only like moderately big, there's a huge difference in speed that you will get between finding one or two of the neighbors using the iterator method versus finding them all right away and then proceeding. Like it's so I can't quantify exactly, for these large scale decisions, I can't quantify exactly what the difference will be. And, so, yeah, so part of what I'm doing is I am going to make a certain kind of array by starting off with a tree. Yeah, yeah. So I mean, I'm kind of splitting the difference here, and I'm going to because I need to do experiments with hopefully larger amounts of inputs. I need some amount of speed to tell that this thing is actually working at all. Because if I write the code too inefficiently, it will take forever to run. It will be too expensive to do the experiments. So I need to have it fast enough that the initial experiments are actually doable. But I also don't want to get super in the weeds with trying to optimize something when I'm not sure whether I really want to optimize this or do it in this way. So yeah, now I'm at the stage where I'm like, okay, I'm also just practicing, good programming practices by getting good at writing code in Python that is as efficient as it can reasonably be without spending a wild amount of time or using additional libraries and so forth that, I'd have to go through and make sure it were, worth the cost of importing them and so forth. But yeah, so I also, I mean, of course, the answer to the questions about like how many nodes approximately, how long does a typical run take, how much memory does it use, I mean, all of these things are dependent on how much, how big the thing is. And so at the moment, I'm just trying to get hopefully a more efficient initial, just examples of this working than what we previously had before. And so, we just knew that the previous implementations were not, were very much not fast and not coded in a way that was at all amenable to that. So once I get this written, I might actually start doing the first, like, maybe not large, but larger scale tests of like how does the space or time consumption scale with the size of the input. So I mean, of course, that's the real question, because everything obviously is parametric and how big the example is that you want to do. But I don't have an approximation for like what that curve looks like. It's not a purely mathematical question, like how many resources. How many resources you're going to use depending on the size of the size of the tree, because in addition to maybe more abstract algorithmic considerations, you also have the fact that I'm running Python 3 on Linux, and like there's a whole big collection of things sitting underneath me that I don't have access to and are extremely organic in nature. So I can't give you I could give you empirical data, but I don't have that yet because I haven't done the bigger experiments. But thanks for asking about that. But I can just remind you, what happens with the code in general. So I need this tree because what I'm going to do is I'm going to make each of the nodes in this tree be like one of the colors in some table. And my goal is to make an array or a table that has a certain special property, which is what I call a dominion in the paper. And so the idea is that I want that if you look in any little 2x2 spot in this array, so they kind of overlap with each other like this, right? Boop, boop, boop. If you look in any 2x2 spot, you're going to find that you have at most two different values there. Is the idea. So maybe a valid dominion would be something like maybe something like this. So if you look in each little box that I can draw, there's at most two different values. Just no matter what little box I choose to draw, there's at most two different values. And so it turns out that this structure is what I need in order to describe the more complicated kinds of polymorphisms that I need to use as the activation functions for my neural net. So in order to make something like this, the way that I do it is by choosing a graph structure on my or choosing a tree structure on my colors or my labels that I'm using, and then only putting labels next to each other that appear next to each other in the tree. Oh, so actually, if I was following that rule for making this, I can put A and B next to each other, but B can only appear next to A or D, so D would be a valid choice here, and maybe A would be another valid choice here. Okay, so that would actually be a valid dominion with this graph as its constraint graph, is what I call it. So naturally, you might ask why, and it's because I need a certain kind of polymorphism of a graph which is relevant to a type of learning task that you might want to do, and it turns out that this table of values that satisfies some table of values that satisfies a rule like this. This is what I call the dominion. And along with a tree like this, which called its constraint graph, having those data together are sufficient to create such polymorphisms. That's enough. It's not maybe necessarily obvious why that's enough, and I should put in some more detail in the paper perhaps before it's actually published, explaining. When I do edits, I'll probably explain in more detail why. I mean, I gave some description of it, but I'll actually maybe give, like a more detailed proof that this does what it's supposed to. But you can use this data together to construct those polymorphisms. And so somehow this data together is what I need for the activation functions. And one reason that I want this to be done in a way that's efficient is because there's some pre-processing work that doesn't have to do with the particular learning task at hand, but just as a general feature of the system, that you want to manufacture a whole bunch of things like this. And so manufacturing a bunch of those, then I should be able to do in a reasonable amount of time. It's sort of something that once you do it once and do it well, you're kind of done with it, but I also want to make sure that I can both create these easily at a larger scale, and also that because at first I probably won't have like a basic library of them built up, and I'm just going to remake it periodically just as I'm experimenting. But also because I want to make sure that they're things that I can access quickly. Oh, hi, yes, thank you. I also want to make sure they're things that I can access quickly because I need to actually use this information in the process of doing the learning, doing training, and so I need this stuff to be readily accessible. So that's kind of where I'm going with it. Are there any other questions, or is there something I can elaborate on? Yes, good evening. Hello. Yeah, so is there anything I can explain, or okay, maybe I'll just actually go back to coding, and then you can let me know if you have a question about something else. But okay, so after thinking about all that, I've decided that I'm going to let me think about this. Actually, I don't think I need the rooted tree at all. Let me think. So the reason that I need the root is because I want to iteratively assign values to this thing for a part of the algorithm. Oh. Yeah, so this is definitely more on the theoretical side, but there is an actual algorithm that I'm talking about here. but yeah, by all means, I hope that you find some, some interest in the paper, and that, it's reasonable. Hopefully, I'll have some. This is the first version that's on, or basically the first version on the archive. I updated it once to fix an image or something, but definitely I'll have edits for the journal that should be publishing it, before too long. So I'm in the process of doing edits now. So that's also why I'm getting back to this, so that I can, have some more detailed experiments to put in there and stuff. But yeah, this is, thanks for checking it out anyway. And hopefully there will be a more readable version with more nice stuff in the not too distant future. Hopefully by the end of the summer. But I'm gonna cross my fingers for that one. Okay, so for some reason, for some part of the algorithm, I need to iterate through the tree and do something. This is my paper. I'm writing code for my paper. This is my thing here. Although as I mentioned, I have had a number of students help me out on this as part of different summer programs, and it's been pretty cool. So I'm sole author on this first paper, but I have a paper in the works with some students right now. Oh, hello. So there's a lot more coming about this, but okay, maybe to go back here for 1 second. So for some reason, for part of the algorithm that comes later, I need to start at a particular node, whatever one I think of as the root, and then I need to make choices iteratively. And the fact that it's a tree is going to help me with that, because if it was not a tree, if it had some cycle, I would have to have a constraint that I would have to satisfy, and I don't want to have to satisfy that constraint because it's just going to make my life harder for some reason. So being able to just sort of do it iteratively, do these, then these, then these, that's going to make my life better. So that's why I wanted to specify a root and have a tree. But what I'm starting to realize is that I don't think I really need to have a tree as a data structure per se. I think I can abandon the notion of subclassing completely, and I'm going to actually not put in a tree as a data structure. So I'm gonna actually abandon that, which is some additional effort perhaps. And what I'm gonna do instead is I'm going to say, well, I'm going to just actually have a method which is create random tree or something like that, and I'm going to construct a graph to have the properties that I desire. And then there's going to be a point in the code where I'm going to need to iterate through the nodes of the tree. So the first thing I'm going to do is where is this picture that I wanted? Oh, no, where did it go? No, it was right here. Oh, I crossed out too much. All right. Well, anyway, I'm going to need to iterate through the. Here, I'll uncross this out. I'm going to need to iterate through the nodes of the tree, and I don't really need a root built in order to do that. What I'm going to do instead is I'm going to choose an arbitrary node, like maybe this one. I'm going to say, okay, I'll start there, and then I'll just look at all of its neighbors, and I'll label them with whatever, and then I'll do this, and then I'll do this. So actually, I can write the code in a way that it will do the tree thing by construction, and then I won't have to actually make a subclass. I won't have to actually make a special data structure for it. And I think that this is what I'm happy with. This also reduces the amount of code that I have to write, which is always a good thing as well. Yeah, thanks. I think one thing that the editors definitely want to see when I submit edits is some kind of more detailed proof or explanation of the philosophical parallel. But it's I guess because I've been messing around with it for a while, it's quite clear to me, and I think that they understand. They accepted the paper. They accepted the paper in the sense that they want edits. So that's we want to publish the paper. So I think that they want maybe more detail on it, but it seems quite clear that these are very similar results. So I now have to just sort of write something a little more formal, saying basically with the general setup that we have in the paper, the these discrete neural nets on finite sets and the usual continuous ones are special cases of the same, general setup. And both of these theorems are theorems of the type that say, like, if your activation functions are polymorphisms of this object, then you can find either an arbitrarily close approximation or an exact, a function that, is expressible in terms of the composition given by the neural net that exactly describes whatever data that you're interested in. And so I'll maybe add some more formal detail to that, but hopefully, if you find it neat, probably that's, making some sense to you already at this point. But yeah, I mean, it's cool that there are some very parallel results in the two areas. Well, there's lots of good connections between math and computer science, and I'm happy to report that it's not only the parts of math that usually are considered analysis or probability theory, but actually pretty much anything that you do in math, there's going to be some kind of application in computing, and especially when we're talking about things like universal algebra or anything that's sort of studying finite algebraic or combinatorial objects, there's going to be lots of applications because that's how things are actually stored in the computer at the end of the day. You're thinking about some kinds of finite data structures or structures that you'd like to manipulate, and so there's a lot of really good connections, and it goes both ways too. Knowing how to code and understanding some aspects of theoretical computer science can actually help you to actually understand what's going on with your math as well. Yeah, they're like little creatures. I used the word organic before, and that wasn't entirely unintentional. I mean, they're not literally organic in the sense that they're not, they're not living things outside of a few, research areas that people do, like living computers in various ways. But, the complexity of what we've produced, both on the hardware side and the software side, is so great that in many contexts it's like dealing with an organic thing where you can try to diagnose its problems or whatever, but you're probably not going to actually be able to take it down into its individual components and analyze every piece. Not because you can't literally do that, but because, if you had enough time, but because you as an individual don't have your entire lifetime to spend disassembling a single machine and understanding how all of its parts work, because that's unreasonable. You can't actually vet every line of code and every piece of software that you're using. It's not going to happen. So coding as part of math research is really fantastic. So there's a balance. There's definitely a balance. If you rely on it too much, you're not going to develop the abstractions that you actually are interested in talking about. I can't tell you how many times over the years I've been trying to code something to find an example of something, and I haven't been able to do it because the search is too hard. It's too much. It's too much resources, and then finally I've understood what I'm asking about theoretically much better, and all of a sudden I can make examples by hand. They were too big for the computer to find. The computer search wasn't fast enough. I couldn't get there, but I saved all those resources by using the resources in my brain instead, and I was able to get it. But other times the computer actually is extremely helpful, and you're able to see that there's a counterexample to something that you've got, or you're just able to see examples, period. It's hard to do arithmetic in some weird algebraic structure that maybe you don't understand a lot about, but you can get a feel for random finite algebraic structures in the computer by messing around with them, and so there's times that it can build a lot of intuition. So like everything in life, I think it's really a balance. It's something that you can't expect to depend on entirely. If you do, you're probably not going to make very much progress, or your progress will be very stereotyped in a way that is not, good math research. But if you don't have the tool at all, there's lots of times when, I just wanted to know if something could be done, or I just wanted to know, I wanted to check an example, and it was very tedious. And for, my peers who can't code, they're just kind of stuck, either asking someone or whatever, and it's just, it's better to just do it yourself. Plus, all the stuff of there's so many times when being able to code lets you automate certain aspects of the workflow that you would naturally have as an academic, like running courses or whatever, that it's really great. So I'm still in the process of doing this, but long term, my goal is, especially for teaching calculus courses, to be able to actually automate the production of homework and exam problems and solution sets more. And by automate, I don't mean using a language model or something, which even if you plug them into Wolfram or whatever, it's it's going to be a little bit questionable, especially because I'm trying to teach students and not expose them to errors that I can't reasonably predict. I want to actually do this manually, but do it in a way that's really automatable or repeatable. And so I've made some progress in that direction, but hopefully, if I do end up teaching more calculus courses in the future, I'll have a really good setup for automating certain aspects of the teaching process, so that I can spend more energy on doing the important parts, which are actually teaching the students, as opposed to writing out solutions by hand to problems that I've done very similar problems over and over, with different numbers or whatever. So hopefully. So there's lots of great reasons to code if you're doing math research, or if you're, in the U.S., you're going to be teaching if you're doing research too. So it's helpful for that as well. Oh, plus making graphics. I mean, of course, making graphics for your papers and stuff is very nice also. So there's lots of great reasons to learn how to code as a mathematician. And then, also you get to have the fun of feeling indignant when people are like, oh, mathematicians' code is so terrible. They don't know how to code. I can never read their code. And then you learn how to code, and you do everything very nicely, and you try to write everything very cleanly and everything, and then you hear this, and you're like, show them that I can code well. But it's okay though. I'm not going to be able to defeat that stereotype, I think. But okay, so at the end of the day, what I've decided is that I do not need a tree class, and that's just going to be work that I don't need to do. I'm not familiar enough with topological data analysis to know what the new developments are. I'm just generally aware that it is a thing that people do. I remember asking people, within the last year, asking people who had some more exposure to it, maybe how do you use the higher homology groups? Are there people using cohomology operations? Is the ring structure actually something that people consider? And the people I was talking to maybe weren't the experts in the thing, but just people with maybe some more exposure than me, and they were basically we are not really using much more than H1. This is the first homology, and no cohomology, no ring structure. There's just H1 is enough in a lot of the applications. And so I had thought about this at some point, just being exposed to the idea. And sorry, this is a little bit of an aside now. And I actually had, if you scroll back in my Mastodon or search or something, I had an interesting conversation with, I think John Baez was one of the people on Mastodon, where I was, basically said something along these lines, and I was like, I have actually thought of an algorithm for using the higher homology groups in using the higher homology groups to actually do, it was specifically the idea I had in mind was a retail analytics kind of application. And so, I had, so this is just the higher homology groups. I'm not, I don't think I ever had an idea about the ring structure on cohomology, but much less the higher operations. But I had described that there, and I mean, if you're curious, you can go look. I think I maybe won't do the whole thing right here. It's not that long, like it's describable in one or two Mastodon posts, but yeah, I mean, uh, I'm definitely. I mean, I'm not interested enough to start a new project, but I'm definitely find topological data analysis an interesting thing that exists, and I look forward to there being more implementations of stuff in the future because, you know, I mean, as much as I love seeing, topology or category theory apply, like applied topology, applied category theory. It's really great when there's the actual application too, not just like theoretically. I've joked like about like doing theoretical applied category theory, where like it's like theoretically there is an application, but that's also pretty different from like actually coding the thing and using it. And mathematicians tend to just be like, well, yeah, of course I could code it if I had to, but like kudos to you for actually doing it. Like that's it is important. Like otherwise, yeah. Um, yeah. So homological invariance for multi-parameter. Um, so like what I was talking about is like if you chose a good scale, and like again I'm not an expert in this area, but like if you chose a good scale, then like my impression is that mostly what people consider to be like an observation is like knowing what like generators for the first homology look like, for instance. But I feel like there's not like maybe there's not as many people that I've seen just casually at least talking about like what the meaning of like the higher dimensional holes is if you choose a good or what the meaning of those holes are if you choose a good scale. So my understanding of persistence is just basically that like for like some large range of choices of the scale parameter, then there are holes that are the ones that stick around for a long time. And yeah, so I mean, is that what you're talking about, or am I not familiar enough to continue this conversation? Or we also just don't have to keep doing it if you don't want to. Okay, you do have an interest in all order homology groups. Okay. So, I see. Oh, and okay, I see. So when you're saying, I understand now what you're saying by multi-parameter persistence. I haven't heard this before, but I definitely think I understand. So the persistence that I was familiar with, that I was just describing, was the one parameter persistence, where you have something that's like a scaling, like that's like a natural number or a real number that's usually non-negative, right? Well, okay, positive really, because 0 is boring. Where you're saying like you're going to put a simplex, a simplex is going to connect, data points when they're all within like that distance of each other. But you now have like some higher dimensional generalization of this, in the sense that you're putting simplices or whatever according to not just one notion of distance, but like a notion of distance that's like a multi-valued thing. Like it's not just like it's not just a one-dimensional thing. That's got to be what you mean by multi-parameter, right? I don't know how you're measuring those different distances, but I mean it's a reasonable thing to imagine that you're. Yeah. Huh. Well, I wonder. Okay, this is maybe we're definitely getting into a bit of a side thing here, but you're making me wonder if So again, not really knowing much about what actually goes on in the area. Like when you're doing just like a single like scaling thing, you have like a family of spaces that are indexed by, um, you know, like your real number parameter, your natural number parameter, whatever. You could think about like, so like when you're saying something persists, like you're saying that, you know, basically that it sticks around for a lot of those parameters. But if you were to think of like taking like your different, each space that you get, you know, as like a different slice parameterized by the distance, you know, that you chose, you could think about gluing them all together or just viewing that distance as like another dimension, and you're really just looking at a single topological space. And it's just that you're not just concerned with like homological information, but it's like a combination of homological information and the size of the actual holes in the direction of the parameter. So I mean, yeah, maybe it's a little bit different if your parameters are higher dimensional, but you could think about having a family of spaces, like one for each value of the multi-parameter, and then gluing them all together according to which ones are supposed to be close to each other, and then saying, well, I really want to understand the homology of this entire object, but in addition to that, I'm going to have a measurement of which of these holes are the ones that are the ones that stick around for more values of the parameter. So they have a measurement of like, for each like homology class, you know, you have a measurement of like which ones are bigger. Oh, okay, yeah, right, okay, and that's the same thing as, yeah, so that's, yeah, right, like in the one-dimensional case, that's like saying that there are natural maps between the homologies of each of the slices. Okay, so, yeah, so you're assigning a vector space to each element of the poset. Yeah, so you know, you can, so like, you can do the whole thing. I guess you're saying it doesn't decompose easily, and I'm not really sure how you want to decompose it exactly, but like, if you look at the category of functors from a small category into, you know, vector space, into an abelian category. Oh, okay. Yeah, so like, A place to I see. So you want to decompose like, you want to decompose that functor into a direct sum of indecomposable such things. Yeah, I mean, I guess I'm not sure about. I see. Yeah, but yeah, I mean, you do have a lot of structure, right? Because you know that you have an abelian category. Like you can do homological algebra to these things. Like that is, you know. Actually, there was, you know, yeah. I mean, if you know you have an abelian category, is like any. Yeah. So like any like small, I mean, does it help you at all to know that like, I've never actually applied this, but I know like this is a thing that like Freud, however you pronounce his name, showed that like any small piece of an abelian category has to be isomorphic to like some corresponding piece of just like a category of modules. So like even if like the category of all such like poset modules that you're looking at isn't isomorphic to just a category of modules in the usual sense, if you're only considered with like a small diagram inside of, there's like a small piece of that at a time, then like, do you know if there's just a translation where at the end of the day you're just asking about modules again, or do you not know of such a reduction? Oh, okay. I'm not actually familiar with the details of the result. I just know that it's like a neat thing that like actually, in some sense, at least pieces of abelian categories can't look like anything else except for categories of modulos. Okay, I think I am going to get back to my code if you don't mind. I know I was the one asking a lot of questions, and so I got us into this. But thanks for talking with me about this a little bit. This will add to my little bit of knowledge where at like parties or whatever, people are like, oh, this thing about topological data analysis. I'm like, oh, I talked to people about topological data analysis before, and like I thought about it a little bit, and like slowly through osmosis, I'll learn the basics of topological data analysis. Um, yeah. My thesis was actually more related to homological algebra, but I've gotten 2 different universal algebra postdocs now, and the homological algebra will come back at some point, I promise. But but I've been doing yeah, absolutely. It's been fun talking about it. Yeah, I mean, like, the more conversations like this you engage in, like you'll slowly accumulate enough knowledge to have like a conversation about it, and you'll be able to picture the things in your head, but you won't have any useful answers when people actually start presenting the actual problems. Um, yeah, I did describe that algorithm on Mastodon though, which means that if that ever becomes useful, I own it for sure. Um, Although if I really am the first person to come up with it, and not just someone who popularized it because I thought of it too, then that means that it'll be named after someone else because of Stigler's law of eponymity. So, um, yeah, there was a big aside about topological data analysis. Um, Yeah, that's how they get you. You stay for the food, and then you know a couple things about the topic enough, and you ask questions, and then people just say, well, I'm not really sure yet. We haven't looked at that. And you go, yeah, I see, huh? Very interesting. We'll look forward to hearing about that. Um, yeah, but okay. So as far as the code that I was writing here, well, I made this look pretty. And I've decided, after much deliberation, to not make a tree data structure. I do need something that renders the graphs into a file. And so, because I need to store my trees that I generate as a file. And so, um, in order to do this, I think what I would like to do is I would like to write a method which writes the graph to a file. So I have to think about how I want to store these things now. So let me take a look at my data structure from before. Okay, so that's that. Okay, so I have like an output folder in my source that's like not something that's not being so I have an output folder in my source that's something that's not being used by or it's not being kept track of by the Git repo, and so that's where like my generic like output stuff goes. And so okay, so let me see about this. This is this. I think what I'm going to do is, in the output folder, for the moment, let's see. So, each line, okay, so the way that the JSON module works is each line is a structure. Okay, so what I'm going to do is I'm going to Yeah, I'm going to store the vertices and edges separately. This is a slight space inefficiency that I think will be worth it for other reasons. Okay, so so then what I'm going to do is okay, write to file. File name. Oh. Okay, so I actually would like to write this to a specific file, and so let's just change this around a little bit. So okay, so it's output, and then okay. Let's just okay, yeah, that's too long. Alright, so I'm gonna write this in here, and let's see. I need my path nonsense. I need JSON. I try to emphasize to my students or just to whoever to write code in a way that doesn't make you expose your actual paths in the code itself. Like, don't hard code your paths into the code. Set it up in a way that everything is like modular, so that you don't have to do that. Because like, aside from the fact that like sometimes people not really knowing a better way or not thinking about the fact that it's going to be shared will actually like drop passwords like directly into code and then forget that it's there and push it to GitHub or whatever. But even if it's just your own like file structure, one thing it's kind of annoying, like for me, I don't really care that much that you can like see my directories. Like you can't, you know, presumably you can't like actually get you actually can't get into you know, my machine to mess around in there anyway, so it's fine if you can see what the directory structure looks like. But it's definitely you know, not good practice to make people have to manually you know, have to do this manually, like to like change what the directory is. Like you want it to just work. Yeah, I mean, it's just you want it to run on everyone's machines the same way without having to change it. I mean, I myself work on this code on multiple computers, and like the directory structure should be something that automatically reproduces itself when you clone, with like minimal setup from like, you know, setting like configuration in PyCharm or whatever. Yeah, so okay, so we have this file, and what do I want to do? What I want to do is that okay, I have a script somewhere where I've shown myself how to do this before, so let me see. let me see if I can just produce that for myself so I can copy the code that I've already written, because I've already written something similar before that's just in a slightly different project. So if I can find that, then I can duplicate the code that I'm about to try to write instead of redoing it. Let's see. I think I know where this code is. This is the other big part of coding, of course, is finding copies of the old code that you wrote previously, so that you can copy various parts of it into the new code instead of rewriting everything from scratch. Okay. This is what, okay, so this is what I want. Okay, so oh, yeah, my YouTube channel. So my YouTube channel is easy for me to remember, so I can actually, oh, well, there's a slash, but I got the easiest handle to be able to remember. So it's just at my name. So it's very easy. It's very easy to, yeah, it's very easy to remember what it is. Yeah. So, okay, so I figured out how I want to do this. I think there's one last thing though, which, well, yeah, I certainly hope that mine aren't random garbage. Yeah. Okay. So, all right. I have to decide how I'm actually, like, okay, I've figured out the method that I want to use, but I have to figure out how I actually want to structure this. Good job, YouTube. Let's see. So I think what I want to do is, in order to make it a single data structure, I think I want to make a dictionary. So actually, I can just do this directly as a one-line thing, I guess. So I'm just going to say, nah, it's not worth making it a dictionary. I'm just going to make it a tuple. It's pointless to make it a dictionary. So the first entry is going to be that, and the second entry is going to be that. That's a tuple of frozen sets, so that should be able to be dumped, I believe. Thanks. Yeah, hopefully, if you're trying to get the energies of the internet to give you stuff that will get you a PhD, hopefully soon I'll progress onto a tenure track job, and then you'll be able to chant into the thing, tenure track. You can already chant postdoc and get me, at least, so I at least made it to this stage. Yeah. So I've gotten 2 postdocs, in fact, because I'm starting my second one in the fall. Um, yeah. So okay, and then we'll put in a new line, and so each okay, so each file of graphs is just going to be a bunch of lines which are pairs that are the set of the frozen set of vertices and the frozen set of edges. And that's what it's going to be. And then that should be loadable as well. So I should be able to load that back into a I should be able to load that back into the appropriate kind of object. Okay, so let's see if this works. Okay, yeah, I think that I'm good. The nice thing about using with here, instead of just opening it, is that you don't have to close it. It closes it for you once it's done. So you don't have to manage the amount of files that you have open. Okay. Okay, I'll make my file name graphs, I guess. Okay. Frozen sets are not serializable. So I guess the question is, yeah, don't ask me about that. So I guess the question is, how am I going to convert it to something that is serializable in a way that's not a huge pain for me? So since apparently I didn't know this off the top of my head, let me look up the list of what is serializable. Okay, I'm gonna have to encode it. I'm gonna have to encode it as a list manually. I see. All right. So it seems to be that the most, unfortunately, the most elegant solution to this problem is just to manually make like tuples out of these or whatever, make linked lists out of these. Okay, but that's not the end of the world, right? Because like this. Okay, so hopefully this should be enough. Okay. Oh. Oh, actually. Oh yeah. No, that, and then. Okay. So that's that tuple. That's that map. Okay. And then I just have to reverse the process afterwards. All right. Let's try this and see if that works. All right. Well, it didn't complain, so that's a good sign. Let's see. So let me now find the actual file and see what we got out. Oh, that's not where it lives. Oh, okay, no, it's here. Okay, so output. Hey, that looks like what we want. That's pretty good. I got a pair of things. I know, it's wild. I got a pair of things, and the first one is the list of the nodes, and the second one is the list of the edges. And so now I just have to reverse this process when I pull it back out. And so each row of this can be a graph. That's good. And let's double check what happens if I do it again. Do I get another copy in the same file? Where is it? Oh, because I'm just using the right. I'm just using the right option, so I'm overwriting. Yeah. The list of things mean you're winning. If you can't express your problem as doing things to lists of things, you may not be winning yet. Okay, so yes, there's one more piece of this that I need to consider, which is I need to actually write to the next line in the thing instead. Did I actually do that in the example that I had previously? Let's see. Oh, it's A for append. Okay. So I do want this behavior because I want to be able to run the same method on different graphs and append them to the same file. So that's what I was looking for, is it's A for append. It's like, what is the option? Alright, now if I do this again, I should get a second copy instead of it just overwriting the first line of the thing. Okay. Where's my folder? Let's take a look at that JSON file again. Oh, and here we go. We made another entry. Okay, so this one's redundant, but I need this behavior in order to be able to add lots of different graphs to the same file, which is what I want. So I'm going to have one file that has all of my constraint trees inside of it. So that's good. So that's going to be pretty. Again, definitely not the most efficient way. If I produced a binary file that just had exactly what I needed in order to keep track of those trees, which can definitely be done way more efficiently directly in binary than as a text file, then I could make it a lot more space efficient, probably more efficient with respect to time as well. But I'm just trying to get something that is a good start. And the other thing I like about this is that it's human readable. So it helps me as I'm debugging the thing to be able to actually open the JSON file that contains the data I'm using and analyze it manually, because that reduces the risk that I've made a terrible error, which encoding things directly into binary you're always at risk that your algorithm is bad, and I need to be able to actually understand what it is that's coming out, and so I definitely, I'm part of the process, so I need to be able to read. I shouldn't increase my own time for me reading the thing if I have to write code in order to parse it and then make sure that my own code for parsing it is correct. Then I'm in danger of having a big problem and not understanding. Okay, so the write to file is done. Okay, so I'll put a capital G for write a graph to a JSON file. Argument. This is a thing that I'm a little bit obsessive about. I write argument instead of arguments when there's only a single one. I do that. I don't write args or arg. I write the whole word argument and I put an S only if it's necessary to have the plural. already, not algebra. Um, oh, yeah, big O notation. Oh yeah, no, but it's important. Besides that it just feels nice and it's good aesthetically. I think it's important to write out the detail about what I'm doing so it's very clear. Because also the more time, yeah. Um, Actually, I truly think the bottleneck is actually me deciding what to do. If you remember, there was a long period of time when I spent doodling around here, and this didn't just have the advantage of explaining to you at least part of what it was that I was trying to do. This is also where I said, oh, I realize now I don't actually want the tree data structure, and like, there's been a series of times where I have sometimes I've explained to you in more detail, and other times I've kind of kept it to myself. But I've gone, yeah, I don't need to do that. If I do it this way, then I won't have that problem. And so that's really, I think, the hardest part, because that's actually me determining what the algorithm is going to look like, and like maybe not the algorithm that's described in my paper, which I already know what it is, but how I'm actually going to implement that, because there are many implementation choices, and that's the hard part. Like, I mean, I already know sort of mathematically what I want to do, but there are various ways of translating that into code, and I'm trying to optimize along several different directions simultaneously, right? I'm trying to write code that is readable. I'm trying to write code that's efficient in the sense of not using too many lines, not using too much space, writing one-liners where I can, but at the same time making sure that it's readable, that I'm doing everything in a way that's very reproducible and understandable. And I mean something that's efficient as well in terms of how long it'll take to run. Not, but if I go too far in any one of these directions, then it'll be too much, right? I'm not going to write an essay explaining how it works. I'm not going to write code that's going to be the fastest thing ever. The one-liner jokes. Yeah. It was a good bit of self-reference too, actually, yeah. That was nice. I appreciate that. Um, yeah. Yeah. So it's optimizing along a lot of different parameters at once, because the advantage of writing good code is that, like, you saw me earlier, like, going to look at code I had written before to figure out how to do this in the correct way. And it wasn't a big thing. It was just remembering, like, oh, I needed this option to append. I want it, dump is the option for JSON that does this. Oh, I had to, I mean, it had to add a new line to make sure it didn't, keep writing on the same line. Like, none of these things were a big thing, right? If I messed around with this module every day, it would just come to me instantly. But the importance of writing good code and keeping things organized and having lots of good exposition is that once you have enough of it, once you have a critical mass, it starts making everything a lot easier. Because, like, yeah, I'm writing this code for this project right now, but this also means that, like, I'm both using some structures that I've already made before, in terms of, like, how I'm doing this process of writing the sort of the redundant data that needs to be used to files, and then drawing from it as I actually do the calculation. But, like, I'm getting practice with so many different things, and I can just copy and paste some parts of this later. I mean, this whole thing is just a module that makes basic graphs and stores them in a JSON file that I can then extract them from later. Like, there are manifold uses of that, math pun kind of intended. There are manifold uses of that throughout the rest of my existence, in math or otherwise, and I have this now, and I made it, and I can extend it, and I understand everything about it. I mean, I don't know every detail about, like, the JSON module, or pathlib for that matter, but I know enough, and, like, this has not too many dependencies, so, like, I understand this very well. Like, the advantage of having, like, hundreds of files like this is unbelievable. Like, it's very nice. So yeah, I mean, definitely this is the way to go. It is slower than copying and pasting a bunch of nonsense from the internet, but it's making me a better programmer. and it's giving me something that I can control and that I can have a lot of confidence in. Okay, well, that's enough ranting, perhaps. So the graph will be appended to the next. Okay, this is also why coding is a difficult thing to automate with language models, because there are many choices that you're making, and it's hard to do that just by completing the next part that looks like it logically follows statistically from what other people have coded in the past. You know, it's kind of missing the big picture, and so it's hard to actually get that kind of optimization. You can see this if you try to take one of those systems and describe a problem to it that is not something that has like the exact question and answer on Stack Exchange, but is something that requires like just a moderate amount of thought. Yeah, and the thing is, you can get stuff that is similar to stuff that's on GitHub or Stack Exchange or whatever, I guess including this, because I'm using GitHub for this too. So you can get stuff like this, but you're kind of just asking for the thing that already exists with a few extra steps, right? Like, it's not nothing, but it's not going to solve these kinds of like bigger problems for you that you actually have when coding. You know, yeah, I mean, it's not realistic to expect that kind of problem solving. It's very close to asking for mathematical problem solving. Like, it's not something that you're probably going to get that easily. It's too easy. Life's not that easy. Yeah, well, however much you feed into it, just feeding more into it is probably not enough. Although if it is, maybe we can have like the robots can take over and we can all go home, right? It'll be like the Matrix, and everyone will be happy, and it'll be fantastic. But in the meantime, I should probably continue working on my own artificial intelligence thing. Okay, so, and that was a joke about everyone being happy in the Matrix, by the way. Although, I don't know, maybe that doesn't sound like a joke to people anymore, but it did back in the 90s, I promise. Alright, well, let's see. Yeah. Okay, so the graph will be added to the next line of the file if it already exists. Alright. Graph is rendered as a pair of lists, since it doesn't think frozen sets is a word, but it's one of the basic data types in Python. Okay. This is just like overleaf not recognizing that combinatorics is a word. It's a math thing. Like, it's like, how can it not be in the dictionary? It's unbelievable. Anyway, somehow a part of me knows that in 10 or 20 years, I will still be getting complaints from the machine of this type that frozen sets isn't a word, and it's a data type in the programming language. Like, yeah, no, morphism, whatever. Overleaf has no mathematical dictionary whatsoever. You can tell that they just used a general purpose dictionary because you'll get things like disestablishmentarianism, but morphism isn't a word in the dictionary. It's like, okay, yeah, I think that I'm much more likely to be talking about math in the math document editing thing than talking about some 17th century French politics or something. Like, there's so many like arcane words from other disciplines that, because they're in the dictionary, they're in some dictionary, but nobody thought to put in a subject matter dictionary. Like, there are technical dictionaries, there are math dictionaries, all it would take is from one person who controls that function at Overleaf one day to say, I'm going to put the math dictionary into the Overleaf dictionary. Like, why would you not do that? I'm sorry, it just continues to blow my mind. Like, why? It's just absurd. Okay. Anyway. Or at least let the users put in their own dictionaries, like whole files, and have like general purpose dictionaries that are shared across your different files that you're working on. Like, that kind of functionality is just not there, and it should be. But for the moment, they have the social capital, and everyone already started using them, so I'm going to continue to pay them money, but I'd like to switch to CoCalc fully when I can. Slowly try to bring people over to that. Alright, anyway, I did the right to file thing. So now I have another choice, which I guess I'll talk to you about. So I have another choice. I can choose to either overload the the initialization function for this class in order to allow it to be created from a file name that points to a JSON file. But it's so natural to be able to put in the set of vertices and the set of edges that I don't think I want to do that. I could use like a class method, but I've never really felt good about those. Yeah. No, there really can't be a good comprehensive math dictionary. It's not possible, but at least certain basic terms can be done. There are math dictionaries, but just by the nature of the thing, it can't really be comprehensive. People come up with new words all the time. Any reasonably cool sounding word has like 4 or 5 definitions that don't all mean the same thing and maybe only have a loose technical relationship with each other. But at least certain basic words that we use a lot should be in the dictionary. Yeah, but there's never going to be a comprehensive math dictionary. Yeah, even just a word list, it's normal, regular, you know. The word dominion has already been used elsewhere, I'm pretty sure. Just basically anything that is a general synonym for like collection, relationship, anything like that. Anything to do with any kind of action or behavior of any type. Anything that sounds roughly like some kind of symmetry or structure. All of these things, all of the words that you can find by those in the thesaurus have mathematical definitions. We do parts of nature as well, but it's not as common, but certainly we have trees, we have forests, we have various creatures. Yeah, absolutely. So that's doable. Of course, like I mentioned, a lot of those words are words that are already in English, like relation, set, class, whatever. But, just take the words like, things like functor instead of, function, morphism, homology, cohomology, just put those, like, there's really not that many at the end of the day. And yeah, people come up with new ones all the time. Like I called something a relator in my thesis. There are things called transfors. There's always like different things like that, but like, just literally just say that any words that are published should probably be in the dictionary. You would think, like one would think that could be done. There's so many things like this where it's like people get really hyped up about like automating all of the things and AI and all of this, and then at the end of the day it's like, okay, if it's so easy to automate doing all of these tasks related to maintaining a piece of software like this, why is this basic functionality not working in the obvious way that one would think that it should? And it's because it's not that simple. It's actually It actually requires some amount of effort that's not easy to automate, and that effort has not been put in because it's not deemed profitable enough, and that's the real story. Like if it was so cheap and easy to automate it, then why isn't it happening? It's like, where's my self-driving car? The answer is that it's not coming. It's not coming anytime soon. Well, anyway. So I'm debating. I feel like just for like philosophical reasons, I'm debating having a. No, I don't want a class method. Forget it. I know what I'm gonna do. Yeah. Okay. I'm just gonna do. Things are happening on the internet. That's good. I'm not gonna make another constructor or do a class method. I'm just gonna do a method in this module. Okay, so my use case is that I'm going to say choose some graph from this file and use it to make this thing. Or no, that's not what I'm going to say. I'm going to say something like, I'm going to make a random tree, and then I'm going to take that tree and I'm going to use it to make a bunch of these dominion things. And then I'm going to store the dominions, and the data that the dominions come along with is the file that the tree is stored in, and its position in the list of trees. So it could be in the first line of the file, the second line of the file, and so forth, right? So what I actually need to do here, if I'm going to... So at the end of the day, what I'm going to do is I'm going to make the random tree, I'm going to make the dominion that's going to be stored in its own separate JSON file of dominions. And then I'm going to, or maybe each dominion will be a JSON file. So each one is going to be a file. And then what I'm going to do is I'm going to, when I actually go to use this, I'm going to say, okay, in order to have a homomorphism, I have to choose for each vertex of the tree, I have to choose a binary relation that comes out from it. And so, storing that data will amount to storing a choice of, let's see, it'll amount to storing a choice of the, for each vertex, I have to have a dictionary that assigns each vertex to the relation. Now, my relations are not serializable, I don't think. And I don't think I would want to store the entire thing like that anyway. No, it would be expensive to package. So you can always package relations into integers, but I don't think I want to do that because I think it's too expensive. So maybe I do want to see if they're serializable. I feel like I remember seeing something that gave me the impression that they might be. So the reason being that, let's see. So it has this class has a notion of, it has a hash, so it has a hash function, and it has a notion of equality. And I feel like I remember seeing some comment that like this was sufficient for JSON to serialize it. So the thing is, okay, I need to store for each of the nodes, I need to store a relation. And so, okay, so I need to load, I need to load individual, let me think about this. Okay, so the place that I'm going to use this is that I'm going to say I make a random tree, and then I make a random tree, and then I use it to generate a bunch of these Dominion files. And then I want to actually make homomorphisms, and so so what I'll do is I will say I'm going to make a new file that I think I'm starting to feel like I can do this without actually having to load the thing that I just wrote into a JSON file. It's still good to keep track of for testing purposes, but I think that unless I want to reuse a particular tree later, I think that I don't actually need to do this, because I think I just create the random tree in memory, I make a bunch of dominions with it, then I make a bunch of homomorphisms that use those dominions. No, I'm gonna want the tree. I understand now. Okay, the reason that I'm gonna want the tree is because I don't actually. I'm feeling a little bit ambivalent. This is like the next big decision for how to structure this thing, and I want to make sure that I'm doing it in a way that's intelligent. So I need to make one of these trees, at least in memory, and then I use it to make these arrays that are like the one that's pictured there with an arrow going to it that says Dominion. So I'll probably make the actual nodes of the tree be ints, 0, 1, 2, and so forth, right? And the dominions will be. Actually, I'm not going to use JSON for it. They're going to probably just be text files straight up that just have the the lists of digits, or maybe they'll be like lists. Oh, anyway, I'll figure that out. But maybe I will use JSON, and I'll just put like the rows each as a separate line or something. No, I don't want to do that either. I need the structure to be traversable without having to load it all into memory, because that's the expensive part. So okay, so each dominion will be a text file that will just basically be like literally a picture of what it is, 0s, 1s, 2s, and so forth. I guess it should be comma separated because yeah, I guess it should be comma separated because that means that if I didn't have that, then I would have to. Alright, well, whatever. I'll accept loading a whole horizontal line of this thing into memory because I think that that's going to be the most efficient way to code it. And hopefully that won't be too bad. Yeah, it just feels really bad though because it's so expensive to read it because you have to bring in the whole line in order to just get that one value. Okay, but I get the value that I want as a specific entry, and then I go to my homomorphism file and I say, what relation is this specific value supposed to be representing? And that's the one that you output. So, at no point did I actually have to read the, at no point did I actually have to read the tree that I made from the file. So that's not going to happen. So because of that, it's actually redundant to store it, which means that I don't need to have that functionality, I think. Yeah. I'm going to store it anyway, because I think it will make for a good diagnostic later, and it is possible that there's cases where I might choose to reuse it, but at the moment, I think that it's actually not necessary. And the reason I've spent so long thinking about this is because that means that I don't have to actually write a loading function, because I actually didn't need the write to file function. I can code this in a way that doesn't require me to do that, and so I'm just going to make a comment here. I'll make it separately so that it's obvious that it's not just the documentation. Okay, so this method isn't needed for the current implementation, but it might be nice for Alright, great. I eliminated that entire thing. So that was a good exercise, but that wasn't necessary, so I shouldn't need to use that. And it's a good exercise because I'm going to be writing some very similar code in a minute. Okay, but that makes my life easier. I don't need to actually... Yeah, I don't actually need to store this. So what am I going to do instead? Let me actually write this down. So, make random tree graph in memory, like in working memory. Make dominions for a tree, store in text files in some way that I haven't decided yet. And then I'm going to make these homomorphism files, but each homomorphism file can work with every... It could just work with every dominion that has that tree as its constraint. Okay, but there's still a way to accomplish this. I'll just make a directory of dominions for this tree, and then I'll make a directory of homomorphism files for this tree. Then I can just go in and say, okay, I want the right, I can just forget what the tree is after that, and I can just say choose one of the homomorphism files, choose one of the dominion files, and just use those together. And that's it. This is fine. Okay, that's what I'm going to do. So, okay, so make homomorphisms for the tree, store in text files. Okay, and so, okay, so I don't actually need to store the tree. I can make it an optional thing if I want to for debugging. And so then, within source, I have output, where all my output goes, and then output, I'm just going to have something that's like, I'm just probably going to just call it dominions, and then it'll be like, I'll probably just have something in here actually where I want to have a consistent naming scheme. So when I write the graphs to file, currently that file is just being put in output. You know what? I'll just hard code it so that these will refer to just like trees.json in the output folder. So the output folder will have a file that's trees.json that are the trees that are being used. And then what I'll do is I'll just have like have 0, 1, and so forth, and they'll just be referring to that line in the file. And so within 0, so for each of these subfolders, I'll have the actual. Oh, well, yeah. Have a good night. Thanks for watching, and thanks for hanging out with us. Yeah, it's a little bit later in some parts of the world than it is here. I'm out in mountain time, so it's like island time but different. Anyway, have a great night. Thanks. Yeah, thanks for watching. Yep. Yeah, you're on the East Coast then. Somewhere. Yeah, and thanks for using the highlight my message functionality too. I'm thinking I'm going to use a different name too. I'm thinking maybe I'll do polymorphisms. Yeah, East Coast, East Coast. Absolutely. Okay, and so then 0 for the tree 0, then that'll have a folder of dominions, and then a folder of the corresponding homomorphisms, and then similarly here. Okay, and so then the idea is that each folder within polymorphisms will represent one line of the trees.json file. I don't actually need to manufacture that file, but I'm going to do that. Okay. So this is currently what I'm thinking for the structure here. Okay. And so that will have the advantage of meaning that this method, okay, isn't strictly needed for the current implementation, but might be nice for debugging. Alright. So I've done that now, and I've dealt with the fact that I actually don't need to make a tree class, but within graphs, I will also write one more function that will be useful, which is create random tree I'll just do a set of vertices. Okay. So let's see what was going on here before. Oh, not there. Should I put it on that? So let's see what was going on here before. So I think there was a random tree thing here somewhere. Random tree. Okay, so what this person did was just pop something off and add, yeah, and then choose a random thing that was already there to make it a neighbor. Okay. Seems good. All right. So so we're going to cast that to a set. No, I guess let's cast it to a list. I actually don't remember if I can pop from sets. Oh no, I can pop from sets. Okay, no, I'm gonna make it a set. Storing the order is not necessary, and I'm not gonna store something that I don't need to use. It's just a waste of energy. Okay. So sets are poppable. Okay, so for my vertices, I have that, and then well vertices. I could say well vertices is not the empty set or something, but the empty set has truth value false. So just well vertices is enough. Like there are still vertices left in the list of vertices. Okay. Oh, here's what I'll do. I'm not going to actually erase this name. I'm going to say new vertices. No. Unplaced vertices. I'll describe it better. Unplaced vertices. Okay. And then I'm not renaming the thing that I put in. And so what I'm gonna still use that as my vertex set, and then I'm gonna do placed vertices. Is going to be just the empty set to start with, and then well, actually no, I don't really. No, I do want placed vertices, and then edges. I also am going to have a set of edges. Okay. And so, while they're still unplaced vertices, I'm going to do stuff, and then I'm going to return graph vertices edges. Alright, and so what am I going to do? Well, new vertex. Well, I'll just call it vertex. No, I'll call it new vertex. Oh, no, I don't want to add it yet. Okay, I am going to want to add the new vertex, but not until I do something else first. So, okay, so old vertex is a random choice from the placed vertices. Oh, yeah, okay, it imported random for me. Okay. So a random choice of the placed vertices, and then okay. An edge between the old vertex and the new vertex. Oh yeah, it's gonna actually iterate through, so I'll just render it as a tuple while I'm still doing that. Okay. So old vertex, new vertex, and then I can add the new vertex to the placed vertices, and then I pop off a new one, and I do the same thing. Yeah, and so at each stage, I'm popping off one of the ones I haven't done yet. I'm making an edge to one of the ones that already exists, and then I'm adding it to the edges that have already been placed, and then I can do the same. Okay, this is perfect. All right, what are you upset about? Frozen set got set tuple any. That's because it's going to be cast to the appropriate type. You're not that smart. It doesn't know. And what is this? Expected sequence. Can't choice just choice can do that, right? Let's see. Well, we're gonna test it. Choose from an empty sequence. Oh, yeah. There's a special case which is something that I haven't thought about here yet. Which is that I have to put something in the placed vertices first. So I popped one thing off. I put this root vertex in here. I have no edges. Alright, let's try this again. I'm going to actually comment this out so I don't keep writing that to the file every time because that's annoying. Oh. I meant a set whose only element is that. Let's see. Are you happy now? Random choice. Okay. Okay. So, you know what? If I'm gonna do this anyway, I might as well just make edges an empty list. because I have to cast it in order to get it to be treated as a sequence for the random choice function. So yeah, so I think it's just better. I think it's just better to just not do that because it's going to be cast to the appropriate thing anyway. Oh. Oh. Whoops. It's not edges. It's not edges that I'm doing this to, it's placed vertices. Okay. So the edges are fine as a set, but I might as well make this a list. That's what I meant. Because I'm casting this to a tuple anyway. Oh, but I did need to. Oh yeah, I did need. I needed an append, but I did it on the wrong thing. Okay. Yep. Oh, but I decided that I was fine with that being a set, so now I have to fix that. Okay, and now we're happy. All right, and now let's turn it up a little bit just to show off now that we've at least made this much progress. So 10 vertex random tree, instantaneous. All right, seems good. Yeah. Okay. So I have my random. Oh, it's still upset about the typing that it's inferred. So I have my random tree. So at this point, let's see. I have. Okay, I've done what was this function as well. Okay, but I've done it in a slightly different way. I've put it in the graph thing, but there it is. Okay. So I've done that. I'm not really sure what this method is doing exactly, because I guess it's saying that if it's the, okay, I guess it's saying that this is this is implemented as being directed, and so it's like a dictionary structure that was saying like these are all the nodes that descend from this one, or something, or that, no, this is, no, maybe for each node it was saying this is its parent, and the root is its own parent, and so it was saying, no, okay, I'm not really sure, but whatever. I've implemented this in a way that avoids having to deal with this notion of the root of a tree, so I'm just not dealing with that. What I'm going to do, I guess when there's one other thing. What I just coded is not actually, no, it's connected. Yeah, so there's no problem. I can choose any node. It might as well be the root. These are trees. They're not forests because I have to, each thing I connect into the thing that I made that's already connected. So like this is perfect. I'm good with this. And thank you for the very nice. Yeah. All right. So my next step, according to my very, very detailed plan that I have here, I made the random tree graph. I can make the random tree graph in memory. So I did that. Now I have to make dominions for this tree and store them in text files. Okay. I'm realizing something. I'm starting to change my mind. Now that I think of it, for testing purposes, what would actually be nice, although it's not strictly necessary, it would be nice to actually have like a file that I make that has a bunch of trees in it, and then be able to say, like, independently, not in all the same run, be able to say, make some more dominions for this tree, make some more homomorphisms for this tree, and just choose whichever ones I want to do. But in order to do that, I will need to load the tree into memory, which is kind of a basic function that you'd want if you already wrote the one that writes it anyway. I've changed my mind. Because it will make testing easier, I think I'm going to do this in a different way than I was envisioning originally. It won't really change the structure significantly, but it's yeah, it's gonna be a thing. So so I think maybe what I'll do instead is I'll say like I'll have a folder which is no, I'm just gonna put the JSON file in the output, and then I'll have a folder that's polymorphisms, and I'll just hard code that this is corresponding to trees.json as opposed to anything else for the part of it that I'm doing. That's what I'm gonna do. There's no need to go overkill on the configuration at this point. Okay, no, this is fine. I realized it's like it's not strictly speaking necessary, but I realized that it's going to make testing a lot easier if I have a loading function as well. Okay, so I'll say is nice for debugging. All right. So that's what I get for trying to type things directly. Okay, it's just going to be filename.json directly in the output folder. File name. Graph number. Is this upset about? Function name should be lowercase, but I want the class name to be capital. All right, you know what? Fine, you win. You win this time. Okay. Okay. So. I'm going to say unprocessed graph. Let me see, how do I want to do this? So I just want to get this. I want to do this in a nice way. Alright, so I don't specifically remember having actually done this before, but I guess what I'm going to do is this just feels so nah, this feels, this just feels undesirable. So people are like, oh, you know, just iterate through the lines this way, but like it just feels bad. Because I don't want to have to break a for loop, and I can say, well, the thing is less than this line, but I feel like the popular answer to this is giving me a little bit of a bad feeling. I have a gross feeling about this, but I guess for now I will do it. I just feel like there's got to be some better way to just read a specific line of the file. Or actually, okay, enumerate read file is an iterable. So I guess what maybe I want is an efficient way to choose a specific entry in iterable. Okay. Like I basically want something that lets me like I just want to I just basically want to, you know, I want to next until I get to the appropriate component of the iterable, and I want to do that in a way that's made to be efficient and not something that's like a cheap trick that's going to be really wasteful, because this feels like something that I should be able to do in a nice way. So I guess first so there's got to be something that does this in let's see. I want to that's not what I want. Because, like, I'd just like to be able to access, like, just like to be able to access a specific entry and not have to break a loop or use a while loop. Let's see. So if I have a generator, I can't subscript it. Okay, so what I want to ask is, I want to know what the most efficient way to subscript a generator is. Oh, okay, itertools. This has got to be more efficient than doing it manually. Works like sequence slicing, but does not support negative values. Okay. Let's see. Yeah. So I was right that itertools does it for me. So I like itertools, as I've said before, and so hopefully their implementation is pretty spot on. Oh, I see. No, it's not literally equivalent to this. It's just roughly equivalent to this. I was reading their code and thinking, oh, okay, is it really that different from? But I see it's roughly equivalent to the code that they give here. So anyway, in case you're curious, what I ended up finding that I think will be more efficient than just doing like the suggested thing from Stack Overflow is this. So this seems to be what I want for slicing an iterable like this, like a generator. I'm thinking that this is the way to go. So if I want to get a specific entry, I could say oh yeah, okay, so then is that what I want? Oh, I guess this. Let's see. Oh no, that's already an iterable that is okay. Whose entries are the lines? I don't need this read lines. I need that read file is an iterable whose entries are the lines. So I should be able to do that and then say. Okay. Alright, so then the question is, let me just do a small experiment to make sure that this actually works. Because if it doesn't actually work, then I will have a problem. So, I'm going to just do a small experiment just to make sure that this actually makes sense. Okay, so I want to slice this. Okay, great. Let's see. Okay, and so in my experiment, okay, no, this makes sense. Alright, so I need graph number plus 1. Okay, so that should be more efficient. Okay, so print this. Now let's test it, just to see if this first part will work. So what I called my test thing before, okay, so load graph from file. Okay, so I guess I'll just do print graph from file, graphs, just 0. Graph from file, missing one positional argument. Oh. Okay. So that printed T, I actually got two things out here. Oh, because I had printed it here as well, so I printed the output of it. Okay, but I get an iSlice object. Okay, now this is gonna be okay. So what I'm gonna do here is then I'm gonna say, okay, well actually, why don't I just return this for now, but I'm actually going to say that this is, I want to do that. What happens if I do that? Okay, and now that's the thing that I started with. Well, for whatever it's worth, this is also one line as opposed to the... Oh, sorry, I just saw the comment here. Did I answer the what are we seeing at this point? So basically, what I was doodling around with for a while was I was trying to figure out a more efficient way to load a single line like I want to deserialize a single line of JSON from this file. I want to be able to say I want this line number. I wanted to do that in a way that was as efficient as possible because I'm going to do this like 800,000 times like a second or whatever, you know, like I'm going to do it all the time. And so in order to do that, there was a suggestion to do this enumerate thing on Stack Exchange, where like you make a new iterable that has like the index and like the line from the file, and you iterate through them, and then you break your for loop or say, well, the line number is less than the line number that you want, just to get there. But I was like, this feels like I want to take a specific entry in a generator, and like I want to like be able to subscript a generator. Like I want to be able to actually choose like the nth entry, and that sounds like something that people are going to have a lot of bad ways of doing, but that the people who wrote iter tools are going to have a very efficient way of doing that is maybe roughly equivalent to some code you could write, just more quickly in Python, but they're probably going to have thought about how to optimize this. And so I wanted to take advantage of that in order to make sure that I was accessing this file as efficiently as possible. So hopefully what I just did using the islice method of, hopefully what I just did is going to be the fastest way that I can access that entry of this file. So I'm just taking the slice of the generator that only has one thing in it, which is exactly the one I want, and then I'm popping that off by using the next method. And then right now I'm returning that, but the next step is I want to deserialize it. So JSON. Do I want load or loads? There is a difference, I think. Let's see. I guess I want loads. Okay. Okay, so now when I do this, well, that should be an actual Python object. And so now I have this pair of things, and so now I should just be able to say graph, and then I'll just pass that entire thing into the constructor. It's a graph with that vertex set and that edge set. There we go. I put all that energy into writing those 3 lines. Those are my 3 lines that load the graph, that load the actual graph data structure from the JSON file. It looks like 4 lines, but this one's just too long. And yeah, this is a little bit hard-coded for my particular situation, but there you go. That's probably a lot faster than hopefully it is a lot faster than what the popular Stack Exchange answer would give you too. Also worth thinking about at this juncture is the fact that if you're asking a language model to write code for you, and that language model is rating how good or useful a particular method is for dealing with something, like how do I deserialize a single line from a JSON file, that the most popular answer on Stack Overflow or something is maybe not likely to actually reflect an efficient or even like a cleanly coded implementation of this. So it's possible that if you look at what's popular on GitHub or what is highly voted for on Stack Exchange, then you're going to get code which is actually perhaps suboptimal. And so, even if there were no security concerns or other things to worry about with asking for like large automated pieces of code, like to just be generated for you this way, it's entirely conceivable that doing this kind of trick is not going to generate what you actually want. The experience that I just had realizing that iterTools probably has done it faster because there's a good chance that they've done it faster because they put a lot of thought into doing these things faster. Like that's just not present in a lot of these things. So yeah, I think this makes me feel pretty good about coding, about myself. Yeah, I'm happy with this answer. Yeah. There is my rant. Now that I've successfully coded this function. Oh, I guess it wants the space. All right. So yeah, I'm feeling pretty good because I need this same kind of method over and over again. Yeah, and I think I'm going to need the same general kind of method over and over again in order to Sorry, I'm realizing something now. I'm going to need to write code like this a couple different times in order to read the files that I've discussed creating. Yeah, I think that I'm just taking a look. I'm just taking a look right now at what other code is actually here. Open this. Okay, so this waits. Okay, so this looks like this is loading the whole thing into memory, if I'm not mistaken. As array. Okay, so it's as a NumPy array. Yeah. Okay. So, right. So there's definitely multiple ways to go about this, and like what was previously set up works. But the reason I wanted to go through this myself, even though it was already done in some form, was both because I want to write my own version because I know I'm going to put optimizations in along the way, but also it looks like what was already done there. Well, it works on a small scale. I don't want to load the entire file into memory every time because these files could be pretty big, and so I don't actually want to be loading it all into the working memory. I want to slice it, and so I'm going to use the same kind of slicing technique actually to, I'm going to grab a specific line and then grab a specific entry of that line instead of loading the whole thing into memory. And my hope is that will represent a really big speed improvement over the previous implementations. So I'm pretty excited about that. Oh, excuse me. I'm pretty. Wow, I might actually be losing my voice. I'm pretty excited about that. Usually I can talk for just 6 hours at a time, no problem, but I actually started to lose my voice a little bit. I can't die until I finish re-implementing these polymorphisms. That's it's keeping me going. Yeah, no, I feel really good about this. I really didn't expect to have this happen live, that I would, oh yeah, no, I have streaming, sorry, in academia, if I try to talk for 3 hours straight, unless someone's working with me very closely and they're really down to do that, in academia, people will be like, okay, but your time has been up, we really need to move on to the next speaker, okay, we're trying to go get dinner, you can't keep going for 3 hours, but here I can just keep going and going, and I do. But yeah, I have plot armor for sure, and it's invincibility because I have to finish this. It's part of the story, so I can't be destroyed while that's happening. So, but to make it more realistic, I'll still take all reasonable precautions to try to keep myself healthy and alive to make the story more engaging. But we really know that it's just fictional. Yeah, I mean, it actually it depends on how long you want to. It depends on how long you want to. How it can depend on how much people are willing to listen to you. Because like, you go 20 minutes over on a 20-minute talk. It just depends on how much people will stand to listen to you. Because like Bill Levere, the category theorist, people would talk about him like going over on talks like they'd tell him he had an hour, and like after 2 hours he'd still be going, and people would just start to leave, and they'd be like, oh, all right, fine, I'm out of here, and he'd just still be going away at the board, like just waiting as people like drifted out or whatever. But yeah, like he would just not stop. Like he would literally just show up and just keep going. They'd like politely remind him, but he was unstoppable. He like didn't care. He just Bill Levere, like Levere theories, the category theorist. That's what I heard anyway. I didn't actually witness this myself, but that's what I heard. Yeah, he just he loved live streaming. Actually, I don't know. For all I know, he could have. I have no idea, but he would have definitely been from a generation that didn't grow up with it for sure, because he was definitely older when he passed away. He must have been born in the earlier 20th century. Yeah, he just passed away a year or two ago. I think. Well, anyway, on that happy note, so I felt really good about this. I have a lot of fun coding, and I've had fun, like, really, truly live coding, like, most of the time this time. I think that was good. I'm still, basically coded this setup stuff in this graphs class and related functions that I wrote here, but you got to see a lot of my process of like thinking about like how am I going to actually set it up, because like I have to kind of have the big picture in mind in order to write the code just for this like auxiliary thing. So it's also it's really helpful because I feel like I really got to like express and record myself like thinking through, okay, how am I going to recycle the elements that I'm actually, like as I solve like little problems, how am I going to recycle them in the rest of the code to reduce the amount of intellectual labor that I have to do. And so I felt really good about finding this itertool solution to reading the specific line number as well. I mean, only time will tell if it's actually really like the most efficient thing to do or whatever, but as far as Python goes, but I felt good about finding that, and that it wasn't like the first answer that came up on Stack Exchange. There's still a lot of skill involved in doing this, it seems. But yeah, thanks so much again for joining me. It's been really awesome as always, and I may continue this next time, or I may do something else. I'm really not sure. I have a lot of fun coding, and I mean, I have a lot of fun, doing math too, like just doing the actual, research itself. But this is a part of it, since this project is a bit more applied, and I just really enjoy coding. It's a lot of fun. Python's fun. I hope you had fun. I definitely had a great time. And I continue to remain invincible, so all is right in the world. Yeah, it looks like I should head out, so yeah, good night. Make sure to have a wonderful rest of your evening. Oh yeah, and thanks so much. Yeah, absolutely. I mean, I always start new things, probably too many new things, but if you can find my email, if you want to shoot me an email maybe, we can talk about topological data analysis, and yeah, please do train a language model to, okay, if you were able to actually make a good, like, live streaming Bill Levere who talked about category theory, I bet you could get it to where like 50% of it is stuff that is actually sensible, but it's unlikely you'd be able to actually have it be like interactive and still make sense. So you'd get like oodles of people who would be like the people who are like interested in math but don't actually like want to like, you know, get down into the weeds and think about the details. And because it's Bill Rivera, they'll think, this is made with AI and it's very smart. It's not that they'll think that it's him, right? They'll think, AI is very smart, computers are very smart, and this thing will teach me category theory, and then they'll just say like nonsense like half of the time, and they won't be able to understand like what's real category theory and what's just like gibberish, and then they'll repeat it to each other and be like, oh yes, I've learned so much. This Bill Rivera live stream is a great thing, and like it's fantastic. And, yeah, no, you could get a lot of people with that. Definitely be more popular than this for sure. Okay, well, enough of me being cynical. I guess I should, I should really, it's just you just have a feeling, and like it's, you know, I mean, what is math if not just, you know, a feeling that you have, and like then that's it, and you're done. Okay, all right. I'm gonna stop being cynical and sarcastic and everything, and get going. But thank you all again. It's been really wonderful. Please have a great rest of your evening.